Hi and welcome to Maths class. Today we're looking at the normal distribution and we're meeting this for the first time. So the normal distribution is a probability density function for a continuous random variable that meets the right criteria such that it will fit the normal distribution. It's a really frequently occurring distribution, which is why it's the one that we study. And a lot of naturally occurring phenomenon will follow the normal distribution. So for example, if we're measuring the heights of anything which grows, the heights of trees, the heights of people, if we're looking at test scores, or for example, if we're weighing bars of chocolate as they come off a factory production, these will all fit the normal distribution. So it's really commonly occurring in the real world. So let's look at some properties of the normal distribution. So what we have there is the frequency curve for this particular distribution. And one of the things that we notice here is that we've got this peak, and the peak is the mean, right? You can see that there is symmetry around the y-axis. The peak is the mean, and it's also the median. So the mean and the median are the same. The peak is the mean and it's also the median. So the other thing that I've just mentioned is this symmetry. We can see symmetry. It says here about the mean. In the one we're looking at, the symmetry is about the y-axis, okay? But that's for a specific kind of normal distribution. In general, the symmetry is about the mean. So the mean is the peak in the middle. And the other thing is that it's got a single peak and it's bell-shaped. So this is called the normal curve, or you might hear it called the bell curve or a bell-shaped curve, simply because it is bell-shaped. Okay, so that's our introduction to the normal distribution. So let's look at it in a little bit more detail. We're going to first look at something called the standard normal distribution. Now, this is not actually one you'll find in the real world, but what we do is we transform those into the standard normal, so we've got something in common to compare it to. So let's look at some properties of the standard normal distribution. The first thing is that the mean, which is also the median, is 0, okay? And we call the mean mu. That's the mean. So here on my x-axis, I've got the mean is 0. The other thing that you can't necessarily see from this is the standard deviation. And this is all in our notes just below. Standard deviation, which is given by the lowercase sigma. And that's 1 for the standard normal distribution, not for all normal distributions, just for the standard distribution. We've got a mean of 0 and a standard deviation of 1. So what that means is that this value here, this 1, that is 1 standard deviation, and this 2 is 2 standard deviations. Okay. So when we have a standard normal distribution, then we use the letter Z for our random variable. So the random variable is always denoted by the letter Z. You know how when we're doing a question and we say, let X equal, and it'll be the number of, sixes if I toss a coin, if I throw a dice 15 times, we call it X, we can call it Y. Whenever we're dealing with the standard normal distribution, we call our random variable Z. And you can use Z as shorthand for saying this is a standard normal distribution. Now, we are learning about the standard distribution before we learn about the general distribution, but we'll get to that shortly. So here's the formula for our standard normal distribution. Don't be alarmed by this formula. We don't really use it a whole lot. Our calculator, our CAS calculator, has it saved. So whenever we ask it to do standard normal distributions, we use Z and our calculator will know what we're doing. And so we don't need to deal with this, okay? But we need to look at it because we're going to see where it's affected when we start to transform it into our general distribution. So the domain is, we've already looked at mean and standard deviation. The domain is the reals and it's got an asymptote at y equals 0. So that means as x approaches positive infinity, y equals 0, and as x approaches negative infinity, y equals 0. So the further away we get on either side from the mean, the less likely those outcomes are. And of course, it's symmetrical about the y-axis, which makes it an even function. Now, it's symmetrical about the y-axis, only the standard deviation is. Only the standard normal distribution is. The general distribution is not symmetrical about the y-axis, but it is always symmetrical about the mean. Okay. Now, this distribution is a probability density function. So let's go back to what we know about a probability density function. We know that the area under the curve from negative infinity to infinity of f of x has to equal 1 for it to be a probability density function. Now, all normal curves are a probability density function. So that means if I'm dealing with something in the real world, which is not going to have a mean of 0, let's say, for example, I've got 250 gram chocolate blocks coming off the production line, and I'm weighing each little block. I don't know, let's say we're going to 3 decimal places on a really precise scale. My mean is probably going to be 250 grams. It might be slightly more because manufacturers often make the mean slightly higher because they won't be criticised then for selling underweight bars of chocolate. You can't be criticised for selling overweight bars of chocolate. So my mean might be, let's just say the mean is 250. So that means this is going to be a different graph. So I have to transform this graph. But as I transform it, the area under the graph has to stay the same. So the transformations are affected by the fact that the area under the graph must stay the same. So these are the transformations that map the standard normal distribution onto the general normal distribution. So what we have first, let's look at x. X becomes sigma x, where sigma is the standard deviation, okay? So that means a dilation factor of sigma from the y-axis. So the first thing that I'm doing there is I'm dilating from the y-axis. So my graph is going to spread out according to whatever sigma is. Now, sigma might be more than 1, in which case my graph is going to get stretched, or it might be less than 1, therefore my graph is going to get compressed. But either way, I'm going to dilate horizontally by a factor of sigma. And then if you look at y becomes y over sigma. So that means that I am dilating there by a factor of 1 over sigma. So my dilation from the x-axis is a factor of 1 over sigma. Now I need to do that vertical dilation in order to keep the area under the graph the same. If I change my horizontal lengths by sigma, then I need to change my vertical lengths by 1 over sigma, so that when I multiply them together to make an area, they will multiply to give me 1. So my total area has been, is preserved, it stays the same. Okay, that's not the only transformation. There's one more there. There is a translation. So there you can see a translation of mu, that's my mean units, in the positive direction of the x-axis. So all we're doing now is we're shifting our mean from 0. Realistically, in the real world, there aren't many things that have an average measurement of 0. And we're moving that to whatever it should be. So if I'm going to my 250 gram chocolate block, I'm going to add 250 in order to move that whole graph to the right. So then the shape and the area is not changed, it's just shifting to the right, okay? So these are my transformations. I dilate it from y, I dilate it from x, and then I translate it to the right, okay? So what I'm going to do now is I'm going to show you the new graph that we've got. Now, I've made an error here. I've got the y-axis shown, but let's assume that the center of my graph now is mu, which is the mean, okay? So the center of my graph is the mean. So this graph is exactly the same as the graph we had before, but now this value here is so what I'm going to show you now is what my new graph is going to look like. Now, just ignore the y-axis, it really shouldn't be there. But in the center of my graph, the x value now is mu, which is the mean. And these tick marks haven't moved, but instead of 1 here now, I've got sigma, which is 1 standard deviation. And because this is the same distance, this is now 2 sigma and 3 sigma, all right? In the negative direction, I've got here negative sigma, negative 2 sigma, and negative 3 sigma. And this is negative 4, and this is positive 4 sigma. So basically, the shape of my graph has not changed at all. The height will be different because I've done that vertical dilation, but I'm not marking in a height. There's no standard height here. So I'm not changing it when I draw a sketch of this nature. But the thing to notice is that a standard deviation is still in the same spot in the shape of the graph. So most of the values are going to fall within this region, and we'll talk about that a little bit more in a later lesson. So this is my new general normal curve. Okay, this is the normal distribution. Okay. So what we did just now was we worked out what the transformations were when I changed my standard normal distribution into a general normal distribution. So what we're going to do now is just undo that and go back from a general normal to a standard normal. So my transformations are going to be in reverse. So my first one, I've just done a translation of mu units in the negative direction of the x-axis. And we can see that here. I've got x translates to, the first thing I do is x minus mu. So I'm moving to the left, and the distance I'm moving is equivalent to the mean. So if I had a general normal distribution, the peak would be the mean. I now subtract that mean from all my x values, and that's going to shift the whole graph along to the left, and it's going to place it having 0 as its peak again. And then I look at my dilations. I have to undo what I've done there. So I had a dilation factor of 1 on mu from the x-axis, 1 on sigma from the x-axis, and from the y-axis my dilation factor was sigma. I just now have to take the reciprocal of that so that I am going back to where I started. So there, I've written it down, dilation factor of 1 on sigma from the y-axis. So my horizontal dilation now is by a factor of 1 over sigma. So that will cancel out the previous dilation of sigma. I'm back to where I started. I'm back to the standard normal curve. And similarly, vertically from the x-axis, my dilation factor is now sigma. So I've followed the order in reverse, and I've done the reverse thing each time. And so that will bring me back to the standard normal distribution. Now this here is a really important part of this formula. It's how, whenever we are given a general normal curve and a general normal distribution and information about the mean and standard deviation, if we do this transformation, we can change it into a standard deviation, a standard normal curve. And we're going to see more about that in later lessons, but I just want to show you what that looks like on my curve. Okay, it's a little bit small, but what I've done there, you can see that I have just lined up these two curves one under the other, and we can see that there is correspondence between similar points. So the reason we have this standard curve is because I can, this was especially important in the days before calculators, to do that calculation for each of these separately using the complicated formula, which we haven't seen yet, I'll show you that in a moment, was really pretty difficult and not something people wanted to do. So what we would have is like a table of values for the standard curve, and then we could translate all of these points up to here and do the calculation. So if I was looking for a calculation, let's say, of what's the probability of falling in this region, What's the probability that my values fall between one standard deviation to the left of the mean and one standard deviation to the right of the mean? I could look up my table, my standard table, and that value would be there, and it would be, the probability would be the same, okay? Because it's the area under the curve is what gives us the probability. These days we've got calculators. It's actually just as easy to go straight from these values and enter the mean and standard deviation that we know. But we still learn the important skill of transforming these values onto the standard curve, and we'll learn more about how to do that in later lessons. So let's go now and take a look at the actual formula. I can make that a bit bigger for you. So if x, one moment, x is a normally distributed random variable, so now we're not calling it z anymore, we're calling it x. I know that the mean is mu. I know that the standard deviation is given by sigma. Then the probability density function is given by this rather ugly looking formula, which we will not use in any of our by hand calculations. But what I want you to see is, see how there's that transformation in there? That's the transformation that takes us from this onto the standard curve, and then everything else is the same, more or less. Okay, so what that means is that for this curve, the probability that x is less than or equal to a is going to be equal to the probability that z, and z is my standard normal distribution, is less than that same a value transformed into the standard value by subtracting mu and adding sigma. Just to remind you where that comes from, it's here, minus mu and divide by sigma. Did I say divide by? I subtract mu and I divide by sigma, which is my standard deviation. Now, if I find that I'm in a question where I've got a standard deviation, where I've got a standard normal distribution, sorry, not a standard, where I have a normal distribution, this is what I write. X is normally distributed. I write down the mean and I write down the variance. The variance is the standard deviation squared. Okay, so that information will be given to you. Well, in the easier questions, it'll be given to you. The mean will be given to you. The standard deviation will be given to you. It's okay to write it, if this is a whole number, if the standard deviation is 3, you can write 3 squared, okay? Because that tells you both the standard deviation and variance at the same time. But this is that in the same way with binomial, when it was a binomial distribution, we wrote this information. Now, again, if you get in there and you can't remember the order to write this in, the safe thing to do is to, oh, sorry, and I left out the all-important n here, which tells us it's normally distributed. Then you can simply write down x is normally distributed, right? Normally distributed, and then just write down mean equals and variance equals, okay? And that way you won't get them wrong. Okay, just to finish off now, what we're going to do is sketch a couple of graphs just by using the transformations that we've discussed. So what we're asked to do is sketch a normal curve with a mean of 2 and a standard deviation of 1. And what we've got in front of us there is the standard normal curve. So just to remind you, the standard normal curve has a mean of 0 and a standard deviation of 1. The curve we're looking for has a mean of 2 and a standard deviation of 1. So remember that the dilations were related to the standard deviation. I'll just go back and remind you. Let me find it. So when I'm going from the standard distribution to the general normal distribution, my dilation factor, both my dilation factors are linked to sigma, which is my standard deviation, and my translation is linked to the mean. So it's the mean which moves me left and right, and it's the standard deviation which stretches and compresses my graph in either direction. So because I've got, I'm just gonna, oops, I didn't mean to do that. Go back to the question. That's it. because I've got a standard deviation of 1, I have no dilations. Because I have a mean of 2, that means that I need to move my graph to the right 2 units. So that's all I need to do. All right, let's try and do a bit of a by hand sketch. I'm going to want a peak of 2 at about here. This is not going to be perfect. And you can see that this asymptote really gets very close at -3, which means 3 to the left of the mean. So here's the mean at 2. So I go 1, 2, 3 to the left. That's where I'm going to get really close with my asymptote. So try that again. I'll pause it while I do this. So that was so bad that what I'm electing to do is actually, oh, where's it gone? I've lost it. There it is. My little cheat. I've used technology to draw it. I need to move that so you can see the working. Okay, there's my new graph. All right, so what you can see there is that my new graph has a peak that is equal to the old peak, a shape that is exactly the same as the old shape, but it's simply moved to the right 2 units, and that's all. And I've got one more example, and just to let you know, I'm going to do the same thing because drawing it by hand was impossible. So in my second example, I'm sketching a normal curve with a mean of 1 and a standard deviation of 2. So now my mean has changed. I'm moving to the right 1 this time. So my mean is 1 and my standard deviation is 2, which is different. So what that means, let's go back and remember our transformations. My horizontal dilation factor is going to be 2. I'm going to double, so it's going to stretch out. And my vertical dilation will be 1/2. So everything's going to get halved. And it has to move to the right. So let's go back to the question. So my height, therefore, well, first let's find the mean. The mean is here. So that's where my peak will be. And the peak will be half the old peak. And if you remember, I said I'm approaching the asymptote here around about, it gets really, really close when x is -3. So I'm now going to be at 6 to the left of my peak because I have to double that horizontal distance. So 1, 2, 3, 4, 5, 6. So it's going to be at -5, which is not even on my graph, but it's going to stretch and looks something like this. Actually, that's not too bad. I'm just going to stick with that. All right. So I had to think of both my horizontal and my vertical dilations, and also I had to move my mean 1 to the right. Okay, that's the end of this video, which was our introduction to the standard normal curve and the general normal curve.